Hello. In this video, we are ready to talk about epoxides. I'm going to explain what an epoxide is, how to synthesize those epoxides, and we'll definitely look at some reactions of epoxides, namely ring opening. Why are epoxides in this unit, though? Epoxides are cyclic ethers. For example, this is the simplest epoxide, a three-membered ring with oxygen as part of the ring. Now, you could have derivatives or variations on this. For instance, you could have some R groups off of the epoxide. You could even have something like this with stereochemistry. Okay. As long as you have this three-membered ring where oxygen is one of the members, that is called an epoxide. It's a general term. Specifically, this epoxide over here, the simplest epoxide, the IUPAC name is oxirane. And we're not going to go through naming of epoxides in this video. What we're mainly concerned about is how to make these types of molecules and how to react them. The common name, though, is what's often used. Common name is ethylene oxide. Okay. If you think about the structure, even if you try to make it with your models, I think you'll experience that epoxides have a lot of angle strain. The internal angle of an equilateral triangle is 60 degrees, so that's far from tetrahedral, which is 109.5 degrees. Epoxides are isolatable, but they're also very reactive. The reaction we're going to see with epoxides is ring opening to break one of these two bonds and relieve the angle stress. And the carbons now, after that triangle is broken, will assume most likely a 109.5 degree bond angle. But we'll get to that when we discuss the reactions. The first thing I want to do, though, is to talk about how to make an epoxide. And we are up to reaction N. Epoxidation of alkenes. Let's take a simple alkene. Let's take propene. Okay. And I'm going to introduce a unusual reagent. It's called MCPBA. And sometimes the M is capitalized, but I typically don't. MCPBA. Okay, we'll get to what that is exactly later. But you want to take the double bond, locate your two carbons. Those are the two carbons that are going to be part of the triangle. And we have this. We know that double bonds are flat. So if we do make a chiral carbon, which we do have right here, technically, what do we have? Technically, we have the wedge version. And I'm just going to draw a line here because that's not chiral. Or we have the dash version, racemic. Let's take another alkene and let's see how the stereochemistry plays out there. Okay, let's take that. All right, I've on purpose chosen unsymmetrical alkenes, and we'll see why in just a bit. Let me use another reagent, CH3CO3H. This might look like a typo, but I really do want 3 oxygens, and I'll show you the structure of this in just a bit. But can you form the alkene with the proper wedges and dashes? See, with a triangle, that oxygen has to be on the same side, or else you'll never be able to close the triangle. Yeah, think of a 3-membered shape, right? Like over here, your oxygen has to be on the same side because these 2 bonds are going to the same oxygen. So these 2 bonds have to be both wedge or both dash. They have to be coming from the same side. So let's draw that product first. Think of it as the oxygen hovering above these 2 carbons of the double bond. That's where the oxygen is, and the methyl group got pushed to the back. Okay. But what if the oxygen is below the pi bond, underneath the desk? Well, if it's underneath the desk, you could draw the epoxide like this. Again, this is racemic. I'm trying to figure out if we'll always have a racemic mixture. No. There are some instances where your alkene will give just one product. We might see that example a little bit later. But let me tell you what MCPBA is. MCPBA is meta. Let me see what C is. Chloro. Okay, yep. Meta-chloroperoxybenzoic. Space acid. Okay. Let me show you how that's drawn out. In my class, you don't have to memorize the structure, but it is going to be useful to know this to see how those 3 oxygens that we see in this reagent are also in this reagent here, MCPBA. The benzoic acid is if there was one less oxygen, okay, carboxylic acid. But this is not a carboxylic acid. This is what's going to be called a peroxy acid. The chloro is at the what's called the meta position, which is down here. You don't need to worry about that. That is the molecule MCPBA, and it is considered a peroxy acid. When you react an alkene with a peroxy acid, you will get the you will get the epoxide. What about this then? Well, that's still a peroxy acid because it looks like this. See how we have in common the 3 oxygens, the carbon, and the hydrogen. Okay, that's how to make an epoxide. You're going to make it from an alkene. There are other ways to make epoxides, but this is the most efficient way. If you could get to the alkene, you could definitely get to the epoxide. Okay. Let's not worry about the other ways to make an epoxide. Those are in your textbook, but again, we're going to use the preferred way. At least I prefer this way. Now, if we think about what kind of reactions an epoxide can undergo, let's take our simple epoxide with a methyl group actually, like this. Let's not worry about stereochemistry. And the thing is, I mentioned that the ring wants to open because there's a lot of angle strain. If we have a nucleophile, okay, there are 2 ways the nucleophile can help open the ring. You can either attack this carbon on the left or this carbon on the right. Let's attack the carbon on the left first, and I'm going to swing all the way around here, like that. The point of attachment then is that dot, but when you make a bond to this dot, that carbon has now 5 bonds, right? Because you know there's a hydrogen here. It only makes sense to break this bond here. Put the electrons on the more electronegative atom of the epoxide. Don't break this bond, and it makes no sense to break this bond over here. That's one option. We'll call this option, oh man. Actually, I'm going to call it option 2. It will be the second reaction that we'll see. What's option one? Option one is, I think, more intuitive. Why don't we just go attack the less substituted carbon, the more free carbon, the one that's unencumbered, and then we break this bond right here. This would be option one. Okay, so those are the two reactions that I'm talking about when we open up an epoxide. Let me grab a new piece of paper. Oh my goodness. Okay. Reaction LMNO. Reaction O. And this will be, like I said, option one. Let me call this nucleophilic ring opening. In the absence of acid. Let's say nucleophilic ring opening of epoxide, actually. And the conditions are absence of acid. Let's pick an epoxide, and I'm going to pick an epoxide that's going to show us a lot of different features of this reaction. So the epoxide I'm going to pick is not symmetrical, has no plane of symmetry, and also I'm going to show stereochemistry. Okay. The nucleophile I'm going to use in this case is going to be sodium cyanide. And again, you're going to have to realize and visualize that we get an Na+, which is the counter ion, to Cn-, which is the actual nucleophile. Okay. The nucleophiles you learned about in Organic Chemistry 1, they have to be familiar because we're going to use those set of nucleophiles on epoxides. We do need some water. Okay, let me show you the reaction, and then we're going to discuss it, and then go over the mechanism that sort of highlights these features. Because we only get one product. We don't get a racemic mixture when we're going to open up the epoxide. The nitrile, when we thought about option one, attack the less substituted carbon. That's the carbon on the 4 o'clock position right here. Not only that, I'm going to make it dash, and we'll explain this in the mechanism, so just be patient. This oxygen is wedge, and this methyl group is still dash. The water is there to put in a proton. That is our only product. It's not racemic. It's one product, one organic product, and not racemic. What can we say? What can we generalize if we saw this result? Well, if this is our result, okay, and we do some analysis, we could say, well, when we reacted with a nucleophile, the nucleophile goes on the less substituted carbon. Not only that, the nucleophile comes from the opposite side of where the oxygen was. This is backside attack. Where have we heard backside attack from? We heard it from SN2 reactions. Let me show you the mechanism. And we're going to have to pinpoint where is this SN2 reaction. Like SN2 means that you attack and kick out the leaving group at the same time. Okay. Again, from Organic Chemistry 1, you got to know. Not the best way to draw CN. Let me draw it again. I'll draw the triple bond. The negative charge is on the carbon. We're going to attack the less substituted carbon. Okay. And you recall which bond to break if I attack this carbon right here. I have to break a bond from the dot to go down from 5 bonds to back down to 4 bonds. And we're going to break this one right here. Okay. That's the SN2. Why do I think, or why do I call this an SN2 reaction? Let me draw the result. Okay, we have this O minus still. The CN comes from the back side, just like a normal SN2 reaction does. I'll put here SN2. Good nucleophile. Less crowded carbon. So if you think about primary, second, and tertiary, we're going to count how many carbons are attached to this dot. There's only 2 carbons. I know it's attached to the oxygen, but technically that's the leaving group. It doesn't leave completely, but it does leave this dot down here. That's what I mean. We kicked out something. The nucleophile came in and kicked out what it's replacing. The CN is replacing the oxygen off of this carbon right here. That's SN2. The last step is water. You could use acid if you want, but water suffices, especially if you have a lot of it. And in the actual lab, you would flood this whole system with water, and just by Le Chatelier, this is going to be protonated, this oxygen right here. Again, only one product, even if we account for all the stereochemistry. We get an alcohol, but we get an alcohol that has this new nucleophile attached to the organic molecule. If we have time, I'll show you some other examples, because again, in this reaction, I can replace this nucleophile with any other type of nucleophile. I could replace it with SH minus, OH minus, BR minus. I could even use a neutral nucleophile like methanol or even water. Okay, so it's one reaction, but if you weren't very I don't know, if you weren't understanding substitution reactions, this is going to be a little bit difficult until you review substitutions of either alkyl halides or, well, that's it, substitution of alkyl halides. All right. I won't have time to go over all the nucleophiles that are possible, okay, but there are videos on my channel that point out what's a weak nucleophile, what's a strong nucleophile, okay? Well, that was option 1, attack the less substituted carbon. Why don't I show you option 2, and how's it going to be different? It's going to be different because we're going to be in the presence of acid. Now, just be a little bit careful. I'm not saying that just because you have acid in the reaction that you'll go through option 2. The acid has to be active when the nucleophile attacks. That's when you do the opposite. Okay. I know it's a little bit abstract right now. Let me show you what I'm talking about. This is reaction P. It's very analogous, but we're going to do the opposite. Nucleophile or nucleophilic, ring opening of epoxide in presence of acid. And again, the acid has to be in the step where the nucleophile attacks. And I'm going to do something very analogous to what we did for reaction O. I'm going to use the same epoxide. And I'm going to use nitrile or cyanide as the nucleophile. But I'm going to use a different version of it. Hydrogen cyanide. Okay, it's acidic. So this is acidic. And what we get is something different. The CN is now going to go on the more substituted carbon. And it's still going to do a backside attack. Did you realize, going back, when I open up this ring, did you realize that this wedge stays wedge? Nothing happens at this carbon. That's why I kept it as wedge. Okay. We're going to see the same thing here. When the CN comes from the backside, this bond stays, and that bond is wedge. You try to draw it as a skinny triangle, OH. What happens to the methyl group? The methyl group got pushed to the front when the CN, think of it as coming from underneath the table. And as the nucleophile comes from underneath the table, it pushes this methyl group forward. Okay. Again, this is not racemic. You only get one product. If you've been taking notes, compare. Compare this product to the product from the previous reaction. Look where the OH is. Look where the CN is. Right? There's that, the first product from reaction O. And then we have the product from reaction P. Now the mechanism is a little more complicated, and also it seems a little bit counterintuitive. Why are we attacking the more substituted carbons? It's so crowded. Why are we doing that? Okay, I'll show you that. Because we're under acidic conditions, we are going to acidify the oxygen first. That's something that we did not do in the previous mechanism. What acid am I talking about? I'm talking about the hydrogen cyanide. This was the step that we did not see in the previous reaction. We protonate the oxygen first. We put the hydrogen on right away. And I'll draw it like this. I'll put the plus charge on the bottom. We created cyanide. You don't have to draw the triple bond, but I like drawing the triple bond. And we attack. We're going to attack the more substituted carbon. So I'm going to swing all the way around and hit the carbon right from right there, because I want space to be able to draw this mechanism arrow right there. We got the CN on the other carbon. And I think that might be it, because the oxygen is already protonated. Let me take care of the oxygen first. Okay. And the CN comes from the opposite side of where the oxygen is, from the dash position, or the dash side. Again, you don't have to draw the triple bond, so I won't draw it here. When it came from the back, it pushed the methyl group forward. Okay, and you can build your model. It's possible to have these groups in these wedge dash notations. Okay. Why? Why do I attack the more substituted? Okay, and why does it happen only when the oxygen is protonated? When oxygen is protonated, you will start to weaken the bonds of the epoxide. The thing is, this bond is weaker because you're starting to build up charge on a more substituted carbon. So when oxygen is protonated, the bigger, partial positive charge is on more substituted carbon, is on the more I'm not saying that we're making a carbocation. Okay, I don't want to introduce that idea. But you are weakening this bond. You're starting to pull electrons towards the oxygen from both bonds, but this position is more stable because technically it's a tertiary carbon. Well, it is a tertiary carbon, and this is a secondary carbon. And we know that carbocations are more stable at tertiary carbons than secondary. But we're not making a carbocation, but still it follows that the bigger, the more stable partial positive charge will start to build up on this tertiary carbon. the bigger the partial positive, the more attractive it is to your negative. Okay, opposites attract. So we can predict where this cyanide is going to be attracted to more. It's going to be attracted more to the carbon that has a bigger partial positive charge. And that's it. On this one page, we're able to look at nucleophilic ring opening in the absence of acid, okay, and then in the presence of acid. What's the hard part? The hard part for this set of two reactions is, well, what are the other type of nucleophiles that we have to recognize? And in the last 4 minutes, I'm going to give you a couple examples, okay? Not only do we have to recognize the nucleophile, like what literally are we going to add to the epoxide, but also where it's going to add, right? And am I under acidic or non-acidic conditions? So look at this epoxide. I'm purposely making it asymmetrical, okay? So we do have a more crowded carbon and a less crowded carbon. My question is, in this first reaction, what is the nucleophile? And do we have an acidic proton acidic enough to protonate this significantly? Okay, this will take some practice, but if you have a solvent like methanol or water, this is considered not acidic. So I'll put that note here, not acidic. You will not have that on the exam. You have to know that this is not acidic. What else won't you have on the exam? You won't be told, but I'll tell you here for practice, that your nucleophile is what? It's OCH3 minus, right? Because you have to break up the ionic bond. So are we using reaction O or reaction P? Okay, that's one question. Let me show you, if this is one of the reactions, let me show you how to get OCH3 on the other carbon. I'm going to use methanol, okay, and I'm going to literally add acid. That's acidic conditions. That's sulfuric acid. The picture I'm thinking about is immediately, am I going to protonate this oxygen or not? You're not going to protonate the oxygen with just methanol. This is not acidic enough. Definitely with sulfuric acid. Okay, definitely with hydrogen cyanide. Okay, these are not solvents. These are acidic molecules. So you'll have two complementary products, one following reaction O, the other one following reaction P. Let me give you another example. I'm not going to show you the answer on the video. This is for at home. But how about this? HBr versus NABR, salt. Okay. See, remember for the nucleophiles, what's a good trick? If you're given NaCN, you got to think immediately CN minus. If you're given NaOCH3, you got to immediately think OCH3 minus. So if you're given sodium bromide, you should be thinking Br minus. Now we need a proton source, not something that's very acidic, but something to give the hydrogen at the very end of reaction O. Right? We need water here. Okay, so you need just a proton source, and I typically use water. That's another example that you could practice with. Again, there are two reactions, reaction O and reaction P, but if you're not comfortable with understanding where the nucleophile is or who the nucleophile is, then this is going to be difficult. The nucleophile here is a little bit tricky than what we saw in reaction P, because your nucleophile is this methanol, particularly the oxygen. Eventually, you're going to have to rip off this hydrogen, and that will be done at the end. Okay, so probably in a practice problem that I'll give you, I'll show you also the mechanism. You should be able to draw all the mechanisms for these 4 problems.